So if you are all here, we start. So this is the book, and I keep repeating, I am one of the co-authors there now. Okay. We have been discussing yesterday about the bipolar transistors. We shall continue with that. I think something we started with a typical BJT. So the basic equations we wrote last time, and very important for us, that the emitter current is always sum of base current and collector current, and this stems from the physics that whatever is injected from the emitter side partly recombines in the base and the rest goes to collector, and because of that base current plus collector current must be equal to the emitter current. Okay. We also said that the collector current, if you are in the active region of the transistor, active means where the base emitter junction is forward biased at least greater than 0.65 volts and the base collector junction is reverse biased sufficiently enough, then we say you are in a active mode of a transistor. Okay. And in that mode we say IC equal to alpha times IE, or essentially IC is equal to beta times IB. This is the law only followed when the transistor is in active mode. If transistor is in cutoff mode, when the both junctions are reverse biased, then none of the junctions are conducting or reverse currents are only flowing. So you may say transistor is in off state. Contrary, if base emitter junction is not conducting and base collector junction is also base emitter junction is forward biased, but base collector junction is also getting forward biased, then both collector will emit as well as emitter will emit carriers in the base. There will be a huge base current. Conversely saying, if there is a huge base current, the transistor will enter saturation. Is that clear? That's the theory which we learned earlier, hopefully so. Okay. So in our analog course, we will neither work on cutoffs nor work on saturated states. Okay. We will see saturation is limit for us. So we will see only work in normal mode or active mode when base collector junction is reverse biased, base emitter junction is forward biased. So all our analog theory assumes that, if not we will tell you what has happened otherwise. Okay. And then we say, in case you are more interested in physics, oh, there is a leakage current coming from IC and everything, so ICO is the current. So essentially what it says, even if emitter junction is switched off, that is VB on is negative, then the base collector current can still flow through base and collector junction, and therefore that's the ICO. Okay, that's exactly what that leakage current is about. So more accuracy can be built in case, but in circuits, let's look at situation something like this. Unless said otherwise, the typical currents will be milliamps and typical reverse saturation currents will be in picoamps. So adding something tens of amps, milliamps to a few nanoamps or few picoamps numerically doesn't matter for us. Okay, that's why we are physics wise. If you say you get out, something, some will shout at, how can it happen? Transistor will never work then. So that's not our idea. Idea here is number, and therefore to some extent we will bypass such certain values in case. But in case your IC is very small, then our I is very small. When it just starts on, that current may add actually. So let's take a case unless said otherwise. We will neglect small currents, but you may write and then neglect saying, oh, I cannot add. So in my circuit we normally don't believe too much. These numbers are great. We also said other day that the collector emitter junction or collector emitter voltage from one node collector to emitter difference is always equal to, because at one node there cannot be two voltages. So if you go through this loop or you go through this loop, so VBE plus VBC must be equal to VC at any cost. Now that's exactly we'll see when the saturation starts, something VC must go down so that VB and VBC must go opposite. That's why both junctions get forward biased. Therefore VBC will become opposite, subtract out of VBE or opposite this, and VC will fall. Otherwise it will always add. Otherwise VBC plus VBC, this will always add to get VC. So if VCB is 2 point some volt, VB is 0.7 volt, so VC will be 2.7 volts. Is that clear? In normal active mode, these two voltages VB and VBC will always add to make your VC. Is that clear? Normal active mode. So this is something we said last time. Now we go ahead and we did something more also. We also showed you some figure. We are interested in small signals. So we said, okay, this the model so far we talked are called large signal models. Okay, the device is swinging in inputs too high and sometimes may not reach into, it may enter saturation mode. So we must take care. And we say our symbolization is capital I small b is equal to small ib plus capital IB, which essentially says the total base current is equal to AC current, base current plus DC base current. And similarly for all, similarly you can also write for voltages. For example, I may write, I may write VBE is equal to VBE plus that is the total base emitter voltage is DC emitter base emitter voltage plus AC emitter base voltage. So you can always say that the DC part plus the AC part is equal to the total current, and that's our symbolization. Nothing very great, nothing, just to say how do we take numbers or how do we express things. We also said if I plot the output characteristic IC versus VC for a bipolar transistor for different base currents, the slope of this characteristics is such for each IB, if we extrapolate them on the minus VC axis. Right now all of us are talking only of NPN transistors. The polarities will change just opposite of that if we talk of PNP transistors. So normally PNPs will not be used as compared to NPN. Why? Anyone? Okay. You said it, but if I say you are wrong, or at least on face you are wrong, why do I say so? The reason why I say so, the current in a semiconductor is, there are two kinds of current transport we have discussed, I hope so. One is called the drift current, the other is called the diffusion current. The drift current is velocity proportional to velocity, that is mu e. Okay. So current is proportional to electric field and the mobility available to you. But in the case of bipolar transistor, the transport is diffusion limited. You are injecting the majority carriers from emitter into a minority, they become minority in the base because that is opposite polarity. Electrons become minority in the base, is that clear to you? And they diffuse, they don't drift there, they actually diffuse. Since there is no drift part there, mobility should not come into picture. It's the diffusion term which should come. But you are not wrong, why I'll say, but in phase you should not say so. Okay, it is the diffusion limited current which is gradient proportional. Okay, how the gradient it creates, J is proportional to dN by dx or dN delta if you are saying 3 dimensional. So essentially dN term by Einstein relation is related to kT by Q into mu. Okay, since D is proportional to mu, you are not wrong, but essentially that's not correct because physics says it's proportional to its current is diffusion limited and not drift limited. So you should always say that it's a diffusion limited current, the gradients are such that it always will dominate. You have very large emitter source here and you have very few electrons the other side in the base, p type, NPN, is that correct? Since they create a huge gradient, the current flows, is that correct? So you are right to some extent that dN is larger compared to dPs, and there also is the gradients normally because of the available dopings of NNP in actual technology, the N channel or NPN currents will be larger for the same area, same biasing compared to PNP. Your statement of it was not wrong, why I said, because fortunately D is proportional by Einstein relation to mu, okay, but otherwise the phenomena wise it's not correct. Okay, so to say, okay, so normally NPN transistor will be preferred as far as we are concerned for, because same area, same everything, I'll get larger current from the same everything. So fair, you know, jitna jada profit, that's what we are looking for. However, I'll leave it to you for you to think later, maybe at the some way I may ask you queries. PNP transistors are never out. Okay. Many circuits still need a PNP. Why? There must be something in PNP which makes it a first choice over NPN. 99 cases, amplifying cases, everywhere you will use NPNs. but certainly some circuits, some blocks, suddenly they put a PNP. Why do they say? Think of it, if you cannot find in a book, if you cannot get to your friends and find, you come to me, someday I will tell you why. Okay. But otherwise, NPNs will be normally used. Okay. So we will not discuss too much about PNP, not that it is bad device or worst device or something. Because of advantages, even fabrication I may tell, NPNs are much easier to fabricate compared to PNPs. Compared. I don't mean very large difference in fabs. So these are all characteristics of NPNs, and if you extrapolate all of them, they end up in a single point, and that voltage we call it early voltage. And this is essentially telling that the base emitter junction, base width is getting punched. Depletion layer from base collector junction touches the base emitter junction, and short circuit can occur. That's the early voltage. That's why current is infinite in fact. Okay. But since the device will become infinite, we will actually shut it off at that point. And there is a limiter, as we say, and therefore no current will be allowed then. Okay. This is what I think I did. Let's do now what is our actual work for the day. We are interested in small signals. I kept telling you why, because the slope of V0 V in characteristic, what did I say? It falls sharply. What is dV0 by dV in your opinion? dV0 by dV in. What is it? No. Think of it, Baba. ऐसा बोलने. V0 V in. This is a device. I am putting V in. I am getting VO. V0 by V in is essentially the gain. If I see a normal transfer characteristics of a NMOS or CMOS or bipolar transistors, inverters or amplifiers, only in this region of V in, you have large dV0 by dV in, that is gain is only available in a small range of inputs. This side gain may be 0, this side also gain may be 0. Is that correct? So we cannot use an amplifier in regions where there is no gain, then why call it amplifier? And therefore, we must operate within this range of DC values, and therefore signal should not exceed either side of, let's say if I bias here, the signal which I put here should not cross these 2 points any day, because otherwise you will get into gain 0 kind of stage or much lower gains at those points. And therefore the amplifier will not act like a good amplifier. Is that clear? So small signal is not that I want, I don't want, I can't do better, and therefore that's the limit which I will always try to follow. However, all said and done, this is fine. We'll like to see what parameters we shall be using in our circuit. The first and the foremost parameter, someone said wrongfully but now it's correct, is the transconductance. Transconductance word says current divided by voltage is the conductance. What is in the output of a transistor? Collector current. What is the input of a transistor? Base emitter voltage. There where the signal is going to be applied. So what do we say? Change in collector current for the change in base emitter voltage is called transconductance. Okay, is that clear? Of course, VB is related to IB also. How? ISE to the power QVB by NKT. This is a diode. So VB is related to IB directly in a diode, and therefore we need not talk current. We should talk about base emitter voltages as our inputs, where signals will be actually applied with this. Is that okay? So because of that, we say change in collector current to the change in base emitter voltage is GM. If I take delta IC of this, I can write delta IC as DIC by dVB into this is partial equation, simple, right? Change in IC to the change in VBE will be DI by dV. This is how you write partial terms, okay? Or delta IC, this is GM times delta VBE. So we say delta IC is what? Change in IC is what? The AC current. Total current is DC plus AC. If I subtract DC part, so what is change is the AC part. So we say delta, capital delta IC is nothing but AC components. So we say small IC, Small IC is GM times small VBE. This is a very important relationship for us. What is it trying to tell? Okay, we may draw a little figure here. I don't know, I'm a left-hander and it becomes difficult for me to keep doing like this. So if this is your base junction, this is your emitter value, this is your collector, let's say I am grounding this. So voltage here, AC voltage here is VB, okay. So if I see the collector current here, it is GN times, is that okay? So the collector current which I will see at the output side is essentially GM times the input signal at the base emitter side, is that correct? This is what amplifier is going to do. Now if this IC current flows through a resistor, IC times that RL will be the output voltage, is that correct? So if I apply a resistance here which is a load, then the V0 is essentially minus IC RL. Okay, why minus? Because our current is GMVB is opposite sign, so it is minus IC RC. But IC is proportional to IB through what term? IC and IB are related by what term? Beta. So I can write V0 is minus beta 0 IB times RL, okay, beta 0. Now I can say what is PBE then? What is the input value you say? I also know, RL, okay, V0 is ICRL and VBE, let's say put a small resistance here, so IB times RI is equal to VBE, let's say there is a resistance here RI, so RI times IB is your VBE, so if I substitute here, I can get V0 by VBE is equal to minus beta 0 RL by, is that okay? Just substitute IB from here and collect the terms, is that correct? And what is V0 by VBE? Gain, AC gain, AC gain, is that correct? AC gain. So a transistor has amplified your input voltage to an output voltage V0 and it can be evaluated if I know the beta of a transistor, I know the load I have substituted and if I know my input resistance. Is that clear? Is that clear? So if I choose RL greater than RI and if my beta is large enough 50, 100, 200, then I am certainly going to get sufficient gain from this amplifier. Is that correct? So a small signal of the value of microvolt to millivolts can get into at least few volts, at least should not be greater than power supply, but at least few volts, and that's what amplification I can achieve. Of course, it's a proportional to RL by RI. The whole circuit theory which will now apply is to get used to this, how do I adjust this RL by RI to get different kinds of amplifiers. This is all that I will do. So basic circuit will remain is this. I have a base emitter input signal and I will get output current. This is my basic thinking because that's what transistor tells me. This is what I am going to use in my circuit analysis. Why do I want to do all this circuit equivalence of that? Because in real life, if I am really solving equations and I write I is equal to IS e to the power QV by NKT, and if I write this kind of nonlinear equations or transcendental equations are difficult to solve analytically. Numerically maybe yes, and every time even numerically take long time to solve. So we say, okay, why do you want to do this? Anyway we are looking at small signals, so we will put an equivalent of something there which represents the actual currents anyway. Is that clear? So all that we are doing is putting an equivalent of what physics is telling in our, so that circuit can be easily solved. And which equations we'll use in circuits? Two Kirchhoff laws, or maybe two more Thevenin's and Norton's equivalents, and nothing more than that is needed to solve any of the circuit in this case. Of course, I will give you some hints. One is called the hint, without solving you can give the results. Okay. There are methods, it's called observation. Oh, this must have this. It may not be accurate, but that may be sufficient to tell me, okay, it has a gain or it has something so much. So how to choose that and how to get that values can be found, but generally circuit is very simple. How many loops you have? One loop here and one loop here. That is very simple to solve. Or two nodes, whatever way, if you want a nodal equation solver or you want the current mesh equation solver, you can solve either way. Is that clear? So 4 equations are all that we need to do analog circuit analysis. 2 Kirchhoff laws and 2 one of the Thevenin's equivalent theorem and Norton's equivalent, nothing more and nothing less. Of course, there is one more theorem. Have you done any course in networks so far? Okay, good. Which is Telegan's theorem. So some other day when it will come, we'll come to you why Telegan was so great. Okay. Okay. Just now I said IC, the collector current, is equal to Is some proportion e to the power Vb by Vt. This is from the theory of a transistor. So if I want to have a definition of GM, I know DIC, just now I wrote an equation of GM delta IC by delta VBE. So I do this, I differentiate this equation, okay, that is what I said, so I will differentiate, and if I differentiate this and I get Is by Vt exponential Vbe by Vt. This is again IC current, so it is IC by Vt. By the way, this Vt will now onwards, that is why I wrote ahead, Vt is thermal voltage, and since few minutes after we are going for MOSFET, their Vt, the turn on voltage, is very important for a threshold volt. We will not confuse with this. So we say, okay, onwards maybe use Kt by Q. Okay, so it is IC upon Kt by Q. So Q IC by Kt. So do you find something interesting? On the left side, GM is what parameter? AC or DC? AC, delta. We have said it's the AC parameter. On the right, Q IC by Kt. IC is the DC current. Is that correct? IC is the DC current. So are you now thinking that the DC current, where the transistor is going to be biased, is going to decide the AC parameter transconductance? Is that point clear? This is the most important fact we must know. The DC bias, that's why I say biasing word, I said the capital IC is going to decide the AC transconductance of the amplifier, okay, and that's most important for us. So if I say I am biasing the circuit for a 1 milliamp DC current, am I not directly giving you GM? If I say temperature at which we are, if we don't specify any temperature, 300 degree Kelvin is what we assume. Otherwise, in some books, they use 25 degrees centigrade, some use 27 degrees centigrade. So assume that normally calculations can be performed to 300 degrees Kelvin, typically 27 degrees centigrade. But if some is using 25 degrees centigrade, then Kt by Q will be 26 millivolts. If you are using 27 degree, it will be slightly 26 point something. Okay, so average we may use Kt by Q is 26 millivolt, which as a number is not okay. Even if you decide to use 25, fine, but use same number everywhere. Okay, Kt by Q is 25 millivolt or 20. Don't write 25.8, 26.43. No use. Why I say you? In circuits, these numbers do not matter very much. Okay, at the end of the day. Okay. So I already said it is roughly 26 millivolt is what Kt by Q are you going to use, and let us say if IC is 1 milliamp, which you are biasing, then the GM is around 38 milliamps per volt. Please remember, GM must not be given, must not be without units. It almost always be specified as amps by volts. Okay. Can you tell me gain should be specified, the voltage gain should be specified by how? V0 by Vn. How should I specify this number? AV. Volt by volt. Is that clear? Please write volt by volt. Is that clear? Why we say so? Because I am going to give you 4 gains later. Okay. some will be volt by I, V by I, some I by V, I by I. So I want to be very clear to people that I must specify the units of gain, V by V or whatever way I am doing, I must specify. Though unit wise we may say V by V is no, because it's the same unit actually. But we must write in analog circuit even if it is both sides same units. Is that clear? This is some symbolization for correct thinking. So this is the typical GM which I am going to get 38 milliamp per volt. This is the transconductance. How will it increase or decrease? Only one expression written here, na? Either the biasing current increases or the temperature increases. Oh sorry, temperature decreases. Okay. So please take it that these are therefore very difficult to, IC of course I will control, but IC is limited by what? Just look at what is the way we started, IC is equal to beta IB. So if I keep increasing IB, IC will start increasing because beta times. But I said don't increase too much. What is the reason I said? It may reach saturation and then there is no amplification. Both junctions get forward biased. Okay. Therefore, IC will reach some maximum. Is that correct? So you cannot go beyond that. You cannot reduce temperature to liquid nitrogen or liquid helium. How can you operate? You will not see the device anytime. Okay. Even your wires may not function at liquid helium temperatures because the conductivity of wire may not remain at 0 or maybe infinite also. Nano it may become otherwise in some materials. So one cannot operate circuits in of course in specific areas in satellite we do cooling as well as heating whenever we need, but normally circuits will be open. Okay. And therefore we cannot play too much on the temperature. In the contrary, we may have worries because temperature will keep rising, and because temperature is rising, your GM will start falling. That means gain will start falling, and that's my major worry. Okay, so I must control my temperature as much as possible. Is that clear? That's the worry which we use. Okay. Coming back to So this expression you have written QIC by KT. There are certain limitations which I have already said, but I may repeat little more detailed way. I already said saturation हो जाता है ना. चलो saturation नहीं भी हुआ. Where are we? Like this transfer characteristics. We may not be here. We may be here. Here also gain is less because slope is much smaller. Here the slope is larger. So now we are in a smaller this and we are moving other side now. Okay. Now here is the case. If I add a input AC signal along with the DC VB. What is it? It is superimposed or modulated. I add an AC signal over a given DC value. That in my hand. I fix VB wherever I want. Then add a signal over it in the input side. Okay, this is an NPN transistor. So I believe if I change VB, the actual VB will be VBE plus Vin because we have added input signal to the DC value of VBE. Then the collector current total will be IS exponential DC plus AC by KT. Right now my assumption is that N factor is 1. Therefore in real life the diode ideality factor also comes. But right now assume N is 1. Okay. And someone should say NKT होता है उधर, हाँ होता है N भी होता है. But अभी हमारे circuit में सब चल रहा है. Okay, so if I say this is the total current and if I take the DC, it is IC is equal to IS exponential VBE by VT. No Vn added. So this is DC, this is total. So what is AC part in that? So this total part is therefore IC times Vn by VT. Just substitute here. So you get total IC is equal to DC IC times exponential Vn by Vt. Is that okay? This term substitute in this. Okay. So you get IC, which is this term, IS exponential QVB by KT is IC. The remainder term is exponential Vn by Vt. Exponential you can always e to the power a into e to the power b is a plus b. Is that correct? The formula which I use is exponential. Okay. So I get IC exponential V in by Vt, and here is that condition which I say other condition why small signals are required. This is exponential term V in by Vt. Let us say V in is smaller than Vt, okay. Input signal is smaller than 26 millivolts, is that correct? V in by less than Vt. I expand this exponential function. What is the way exponential function is expanded? 1 plus x 1 upon factorial 2x square plus 1 over factorial 3x cube and so on and so forth. So if I expand this term, I get 1 plus V in by Vt, half V in by Vt square plus factorial 3 means 6, 1 by 6 V in by Vt cube plus so on and so forth, higher terms. Is that clear to you? Is that clear to you? What do I say? I just expanded this exponential function in the series form, okay. If you now say, and we also know the small AC current is total AC, IC minus TC IC. So you see from here, if I subtract this IC minus IC, 1 plus 1 will cancel, 1 will go away because IC will subtract. So if I do that, I get IC is equal to IC by Vt times V in plus half IC by Vt square V in square plus 1 by 6 IC by Vt cube V in cube and so on and so forth. Is that clear? AC current, how many terms I am getting? First is the major term, which is first order term. This is second order term. This is third order term, and there will be n order terms if we. Now you can see, if your V in is closer to Vt, what does that mean? Or larger than Vt, the second order, third order terms will start increasing or even dominating. Is that correct? Is that point clear? So now you are trying to say that if that happens, the gain should really increase because you are getting more and more terms out of it. But really what will happen? Gain will finally go to 0. Okay. So what is the condition that this only term comes to our requirement, which is called the fundamental term? V in should be very, very small compared to Vt. Then these two terms and all higher order terms can be, if V in by Vt is smaller, much smaller than 1, then we can say the second order, third order, nth order terms are negligible. Is that clear? Is that clear? If that happens, IC is equal to IC by Vt times V in, then the GM is IC by V in, therefore it is QIC by KT. And if you want therefore this GM equivalent circuit to stand, which we did earlier, condition is what? What is the condition on input signal? It should be smaller or much smaller than 26 millivolts. Is that clear? Two ways I explained you. One is from the transfer character I say no, you will get harmonics out. Even without that I say normal thinking, I can prove that I cannot exceed too many, because remember V in will be sin omega t. Okay, sin square omega t means 2 omega t mein omega 1 plus omega 2 omega 1 minus third order terms will start appearing. Is that correct? So you must understand, in this there is only one omega t term going on, which is called fundamental. I have a signal at one frequency and I want output also at the same frequency. If the power or energy is given to other harmonics, I will not get enough power for my fundamental. So my amplification will become lower and lower and lower. Is that clear to you? So the second and third, yes. Because the biasing is such done that we always remain in that region. Okay, that's exactly what that's why I say biasing word is very good. That's why we are going, because I want to go to circuit quicker, but I want to make you clear that why I actually restrict myself every time. So this is only few lectures I am taking for you, modeling, so that you know why I cannot do more or less than this. This is what is only possible for me. Is that clear? So those limitations is only I am trying to come to. If I go out of the ranges, what you say will happen. And physically what can happen is I may actually get into power and energy into other frequency terms which I don't want. Is that correct? Let's say total power is so much, if I give 80% to other harmonics, I am get 20%. So I must restrict that. Is that correct? That's the idea behind it. Okay, very good. So is that small signal word is clear? Why small signal? Why analog people do not want to talk too much about large signals? Is that okay? Is that okay? So this is only to prove my points that why I sometimes do something which I say okay. Yes. No, but because the output which you will put will have some RC time constant, so it will only address to those frequencies, one frequency. One RC is the time, that is frequency. So at a given this, it will only respond to a frequency. Okay, what you are saying is not very absurd or wrong. If I can tune those other harmonics, that's what we say, yeah, power can be pumped back, but then you require additional hardware to do that, which is what in microwaves we do that. The higher harmonic terms we actually convert back to fundamental, but there is a huge circuitry to do that. Okay, so we lose power in converting back. Okay, that's the idea, but that is doable. You are right. Okay, let's look into the other things of the BJT. So far we looked into only one parameter. Which one? GM, which is our major parameter. So we say okay, पहले उसको देख ले. अभी दूसरा टर्म क्या बोला था मैंने अपना एनालॉग के लिए? बैंडविड्थ. Is that bandwidth is something to relate with some output gain or gain of this amplifier remains constant till certain frequency. Okay, so we are looking for now frequency response. Whenever I go, just now I said to him, frequency word comes, time constants are associated. Is that correct? 1 upon RC, 2 by RC is time frequency. So whenever I say frequency, I am looking for RC terms. Okay. So now I must look on to two more terms. GM of course is the transconductor. Now I must look for R as well as C's because I am now looking for bandwidths. Gain I know GM will probably help me out. Okay, but I also want bandwidths. So I want to know how will I control that or how do I go. In a small signal, Vn is applied as the circuit I showed you earlier. Then we say delta Vb is small, again repeating, is Vn delta. Similarly, the charge which electrons will inject, emitter charge QE, change in emitter charge is small QE. Similarly, change in base charge is small QB. But charge neutrality in transistor in a steady state, what does it say? The change in base charge should be same in emitter charge change, because otherwise what is injected cannot remain, can't increase there, neutrality must hold. So at then we will say small QB is equal to small QE because neutrality has to hold. Okay, but right now I am giving separate names. Finally I say okay, QB is QE. Okay, but to make a point I have separated because in real physics if you have done it, they will say the base cannot increase the concentration electrons in it because they must recombine, because otherwise charge neutrality will be violated. Is that correct? So that term is valid here also, but just to make a point I am not changing. So we define a capacitance which is related to base emitter junction, and that is given by the change in base charge divided by input voltage. Q is equal to CV, no great things, still 7th standard physics. Q is equal to CV. In JEE, I don't know now because of this tick marking system, otherwise we used to have many problems in this charge and capacitance, Gauss's law, point to point. At least in older JEE in our times, there are huge problems in electrostatics. I don't know how much part now in your newer JEEs. What is the purpose in newer JEE? To get 8,000 people. Okay. Earlier we used to reject beyond 400 only, so 7,600 must go. Okay. So थोड़ा rejection system पहले ज़्यादा था, अभी थोड़ा selection system है. Good. Now we say the change in emitter or emitter charge is nothing but the current times time, or Q by T is current. Is that correct? Charge by time is current. So emitter current which is received at the collector side through a transit time which is called base transit time. Remember, electrons are injected at base emitter junction, transit through the base, are collected. So there is a finite time which we say base transit time. Transit time, please say it's not minority carrier time. What is it called? Transit time, time taken from here to here, base transit time. So whatever received is collector current, so collector current to base transit time must be the charge injected from the commuter side. Okay. So similarly we can also say delta QE is tau B times delta IC. Why is this delta that I am adding? I want to make AC part in that. As soon as I add delta, I get an AC value. So delta QE is equal to tau B times delta IC. Please remember, I said right now here, delta QE will be equal to delta QB. Why I said so? Charge neutrality hold, always be held. So we are interested to know this CBE. What are we trying to do? We want to now show you an equivalent circuit. So any component which will change my bandwidth of the gain, I must find. So this is first thing. After GM, I want to see the capacitances. So delta QE is tau B times delta IC. Is that okay? Is that okay? You just say, otherwise I'll wait till you write. Okay. Delta QE is tau B times delta IC. Now this tau B in devices is what? Anyone? Remember device theory last semester? It related to what? अभी बोला ना मैंने यार. You just think of it. This is my base width. यहाँ से आया यहाँ ये टाइम है. क्या किस पे डिपेंड करेगा? Base width. Larger the base width, larger is the transit time. Smaller the base width, smaller is the transit time. Is that correct? Is that correct? So obviously tau B must be related to base width. Okay, is that okay? Since I say delta QE is same as delta QB, so delta QE is equal to delta QB is delta IC tau B, or QB is IC times tau B, and therefore the CBE, which is called, by the way, this CBE is called diffusion capacitance. What is it called? Diffusion capacitance. Why it was called diffusion capacitance? It's related to diffusion phenomena of carriers in the base. Is that correct? So it is called diffusion capacitance. It is not a junction capacitance which we have to calculate so far. It's only a carriers moving, charge is changing. Any change in the charge means capacitive effect is there. That's why charge changes. Is that Q is equal to CV. So if charge changes, there is a capacitance, and since charge is proportional to the voltages I apply, therefore capacitance is varying term. Okay, so CBE is also sometimes called C pi dash, is QIC by KT in tau B. And what is tau B now? WB square by 2dN. WB is the base width. So smaller the base width, smaller is tau B. Smaller is tau B, smaller is CBE. CB is between base and emitter. So what will happen? If CB is smaller, what will happen? For a lower frequency, what is the impedance it will offer if CB is smaller? For lower frequency, omega is smaller, CB is smaller. Impedance is very high. If this impedance as seen from the input side is high, what does that mean? Equivalently saying, is it important or not important? If input impedance across two terminals is very high, is it important or not important? Not important. It's like an open circuit. It does not play games. Is that correct? Whatever voltage you are current applying, it will pass because it's like a high head sitting there. However, if omega is higher and CB is higher, then what will happen? Then this shunting effect will start, short circuiting will start. If omega is larger and CB is also larger, that is the base width is long enough, okay, then Zn will be very small, and then whatever I will pass through this will be divided. And in worst case, if this is very small, everything will go through it. Is that correct? No divider there. Currents will just go through shorts. Okay. Therefore, is that now clear why I am interested in CB? Because for my given operating signals and at frequencies, I want to see whether this capacitance will have any influence or not have influence. Okay. So I must know the value, because if I get the value, then I will say, okay, omega C will decide whether it is required or not required. Is that correct? but I must know first what is C. Is that correct? That's the effort. Is that point clear? Why I am doing this? Because I don't know if otherwise if I increase my input signal frequency to 100 megahertz, nothing will go to the output, everything is here shorted out. Is that correct? So input is not allowing signal to get in. Is that correct? So I want to know what is that limitation. Am I reaching that? Okay. That's why I want to know the value of CB or what is called the diffusion capacitor. But that's not the only capacitor there. We'll see another one. Is that point clear? Why I am doing this? Okay. Coming back, few more things we should like to, we come to other capacitance, but let's see the other two major worries about it. I just now say for bandwidth, what are the important terms I said? R and C. One of the C I saw, see other C's also, but let's see R quickly first. I am also interested at the looking at between base emitter, what is the resistance offered. The same logic will go. If the resistance is very small, what will happen? By same logic, if this resistance is very small, any signal going from here will be shorted out. Nothing will go into the circuit. Is that correct? So what do I expect this R to be? As high as possible. But I may not be able to control for variety of reasons very high value. Then at least I must know how much is this, so how much is really made available to me. At least that number I want to know. Okay, I don't mind, it is there. But how much is there, at least I should know, because then only I know what is I am going to get here. Is that clear? So I must evaluate the normal input. This is not external, which values we are calculating, simply because the transistor sitting there. Further additionally, externally, what we'll do will make more mischief for us. But at least internally what is happening, we will like to know. So we say IC is equal to beta times IB, our standard active region equation. IB is 1 upon beta times IB, again use delta IB. So we write D by DIC, IC of beta. We define a AC beta as delta IC by delta IB or small IC by small IB. This is called AC beta. Is that clear to you? So far earlier what beta we defined? Here this beta and this beta are not same. That is called DC beta. What is DC beta? Capital IC by capital IB is DC beta. You apply DC signal, DC voltage and you see what is output. So the collector current divided by base current is DC value. This is DC beta. If I now substitute in this equation, I get IC by IB, which is beta 0, delta IC by this. However, in this differential, if beta, DC beta is constant, please look at the case what I am saying. If DC beta is constant, this beta can come out. Is that correct? In differential it will not be useful. Then this will be 1. So what is it trying to say? AC beta is equal to DC beta if beta is DC beta is constant. So in your design or in your circuit, you must ensure if you are using same values of beta, that beta is constant. Why beta can change? Can you tell me? You have done devices now. Beta can change because of the two things. Base width is correct, but I am looking from external. You are right, base width is major because that's the beta factor. Directly it will decide alpha T. Okay. Temperature, you are very good. It also will be limited by the currents which you are passing, levels of current. Beta falls as current increases. As IC starts rising, the beta will start falling. Initially, as collector current rises, beta will rise. थोड़ा physics फिर से पढ़ो. It will become constant for a great time, and if you further increase IC, it will start falling. Okay, because of the emitter efficiency and transfer factor effects, temperature effects, beta is not constant. So where you should therefore operate? In those IC regions where beta roughly remains constant, you can use DC beta as same as AC beta, and therefore operation of, that is the DC biasing, again is very important, because I don't want to always separate DC and AC beta. Is that clear? So I am giving you why we operate only this much, because otherwise we are not sure what values we are actually going to get. Okay. Okay. Is that point clear? DC beta will be equal to AC beta as long as DC beta remains constant, and that is the way we will actually make circuit to work. So that AC beta value, so if manufacturers gives you beta of 200, I don't have to recalculate what beta I should use in my analysis, because I'll see I'll operate by my conditions that beta remains constant. Okay. The next thing which we would like to know is the input resistance. I mean, from this we want to know actually input resistance. What is input resistance? Will be input signal or AC input divided by base current there. Just now I showed you. So it is V in by IB, but IB now can be written as IC by beta, and now beta can be beta 0 or beta DC, whatever you wish, because we have made sure that beta is same for both cases. Is that clear? So if I substitute IB by IC by beta like this, but what is V in by IC by V in? Just have defined earlier first term, first parameter, GM. IC by V in is GM, so it is beta 0 by GM. Is that, and GM is related to what I said? Which by thing in DC I am connected to? Collector current, DC collector current. I know the bias current, I know GM. I know GM, and if I am ensuring you beta DC same as beta 0, transistor will tell you what is beta. So I know my beta, I know where I am operating, therefore I know my GM. So I also know my input resistance R pi. Is that clear to you? R pi is equal to beta by GM, or to say this is very sacrosanct relation, beta is GM R pi. Beta is GM R pi. This is a very good relation for all AC analysis for transistors. Is that correct? Conditions why we said DC AC constant, otherwise we may have to both. If I now substitute GM and R pi values as we did, one can show from the way I have written here, R pi is nothing but KT by QIB. So whatever your base current, which is proportional to ICY, IC by beta is IB. So if you know your base current, you also know your input resistance. Is that correct? Or if you know your bias current IC and you know beta, which is saying IB is known, you know your input resistance R pi. Is that clear? So R pi is not a constant quantity, it is variable. With what it is varying? The biasing current. So is that point got into all of you, that bias current? No. Anything add you do it, it will cannot be added across the junction internally. How do I get inside the junction? ट्रांजिस्टर के अंदर तो आप हाथ नहीं डाल सकते, बाहर टर्मिनल में अक्रॉस क्या कर, तो बाहर से लगाएं तो और कम ही हो जाएगा. एनीथिंग यू पुट ए पैरेलल टू दिस विल बी लेसर देन दिस. इज दैट क्लियर? सो एक्सटर्नली अंदर की चीज को हाथ नहीं लगा, एक बार पैकेज मिला खत्म. So I must know what is in. That's the idea. Is that clear? If I have what you are saying in a way is that during your fab, yes, I can do something. But once I fab it, that's the end. That's the fixed value. Whatever dopings I used, whatever process I go through, that will be fixed for you now. I cannot do anything on that. Beta I कर दिया मैंने, बेस विड्थ फिक्स कर दिया, बेस एमिटर जंक्शन के डोपिंग फिक्स कर दिए, टाइम ट्रांजिट टाइम फिक्स कर दिया, माइनॉरिटी कैरियर लाइफ टाइम फिक्स कर दिया, सब फिक्स हो गया, मेरे हाथ में कुछ नहीं. Externally it's going to spoil something, but that's what the limit is coming. This is internally itself creating a problem. So first we must like to say what is internal to us, and then equivalent circuit when we'll make, the transistor will be replaced by all this together, and then externally we'll put whatever we are actually getting in a circuit and then solve whole of it. Is that point clear why I am doing it? I want to represent this transistor as if it is in a circuit form. Okay, otherwise वो ऐसा कैसे है, उसमें क्या मॉडल रखें ना. I cannot write IC is so much cosec HW by LV plus cot H something. That equations I cannot write for transistors, okay, in circuit. So I want to put everything in circuit form. So this is also one value which I want to know equivalently. Okay. Very good. The second parameter to us is R0. Okay. What is it? Output resistance. अभी input देखा ना? Let's see at the output side. What is the resistance I am saying? That circuit which we did, GM BBE, ये कलेक्टर है, एक यहाँ भी R0, ये शंटिंग क्यों होगा? Why it will be shunting? What is this? क्या है ये? करंट सोर्स है, उसका एक रेजिस्टेंस शंट होगा उसके आगे. हाँ, तो वी वांट टू नो व्हाट इज दिस. बट कैन यू कन्वर्ट इनटू सीरीज काइंड? विच थ्योरम? नॉर्टन थ्योरम से थेवेनिन में जाओ, GM टाइम्स R0 वो करके R0 सीरीज उसके इक्विवेलेंट R भी निकाल सकते हो. बट राइट नो वी आर ओनली इन द नॉर्टन्स इक्विवेलेंट साइड. ओके, so I want to know what is this so called output resistance for me, R0. So I said okay, just now I did delta IC is delta VC into delta VCE. Okay, delta IC can be written in a interesting form, delta IC in delta VC into delta VC. No maths, ये दोनों same term है, but we can always write like this. But this term delta VC by delta IC essentially is अर्ली वोल्टेज. आपको बोला था इसका जो स्लोप है वो अर्ली वोल्टेज है, सो VA बाय IC. इसका जो स्लोप है वो अर्ली वोल्टेज डिवाइडेड बाय IC. इज दैट पॉइंट क्लियर? इज दैट पॉइंट क्लियर? सो इफ आई स्पेसिफाई टू यू द अर्ली वोल्टेज 20 volt 50 volt, then what, and I am saying I am biasing at this bias current of IC, what I am giving you? R0 value. Is that clear? Is that clear? If I am specifying early voltage, this is 50 volt. Transistor has a early voltage of 50 volt. Okay. And if I say I am biasing at 1 milliamp, so कितना R0 बोला? 50 by 1 milliamp, 50 kilo ohms. So as soon as I know my bias current, I am actually telling what is R0 I am using. Okay. So please remember every time which term I am connecting everything to the biasing current. Is that point clear? Everything I am connecting to biasing current. So what is important in analog circuit design or in analysis? Where you are at IC, which value of IC you are operating at. That decides everything for you. Is that okay? Is that okay? IC is the DC IC is the major parameter for us to get, so that we know what is the final circuit equivalent we are going to get. Is that clear? Okay. So anytime early voltage is given to you, which we will specify to you, 20 volt, 30 volt, 40 volt, 100 volt, can be even 100 volts. Is it good or bad if it is 100 volt? नहीं, good तो है, number बड़ा इसलिए नहीं. What is the reason I said? You are right. Larger the early voltage, good for us. Why? R0 will be larger. In a current source, what should be the parallel resistance? Preferably or ideally? Infinite, ideal current source. So larger the R0 you are going to get, closer the good current source you are going to get. Is that correct? And that's why we will be very keen to get larger R0 if possible. Okay. Other possibility, I may reduce IC. But if I reduce IC, what I am going to reduce? GM. So मेरा gain गया उधर से. So I am worried. I cannot too low, too high. Is that limitations clear to you? I mean, I had to worry everywhere. If I want this, I may lose this. If I want this, I may lose. So somewhere, what do I get? That's why all these theories are again brought to your front. Okay. Is that R0 clear to you? VA by IC. Normally, these values will be specified to you. Is that okay? Yes. IC is the collector current. Say you are biased on this. Any point here, actually it is VA plus VC. Small. Let's say your point is taken. Okay, you are biasing here. Okay. Sorry, it's not a straight line properly. So actually this value plus this value divided by this IC is the slope. Is that correct? But what I say, how much is VC will be? Less than power supply value, few volts. How much will be VA? tens and 50s or hundreds of volt. So in calculation VA plus VC divided by that, instead you can always use VA by IC. Is that point clear? What he said probably I should have said. Is that clear? In reality slope is this by this, na? Okay, this is little smaller compared to bigger values. So maths, nothing more. Okay, there is another term which transistor people keep talking, is called eta term. Okay, it's not NKT kind, it's a eta. Okay, and very important factor. It is decided as, it's defined as KT by Q 1 upon VA, where early voltage. Theory we can do someday if you wish. And if I substitute KT by Q, please do it. What is the, why I write all this fun? We can directly write this. KT by Q, एक IC इधर रखा, एक IC ऊपर रख दिया. Same है ना? But this is 1 upon GM, this is 1 upon R0. So GM R0 is a figure of merit, eta. GM R0 is 1 upon eta, is a figure of merit for a transistor. Is that clear to you everyone? GM is for a given, see IC will decide GM and IC will also decide R0. Is that correct? Therefore GM times R0 is a figure of merit. Is that correct? It is 1 upon eta. Very important parameter in design. Not in analysis so much, just to show you how. So I actually searched transistors which has smaller etas. Okay, that means larger GMR0 terms. Is that correct? So when I go into the so-called manuals of transistors and I am looking for higher gain bandwidths, then I should look for transistors which has higher GMR0, essentially smaller eta values. This is specified, these are all figure of merits. Okay, is that point clear? Is that clear? This is something someday you design chip or circuit and you open a manual from a company. You should know what you should look. Okay, that's why I showed you. Okay, typically eta will be order of 10 to power minus 4 minus 5. Smaller the value, better is GMR0. So if you use given beta values, typically R0 values which we have got here for early voltage of 100 and 1 milliamp current, how much is R0? 100 kilo ohms. Okay. If it is 100 volt early voltage and 1 milliamp current, 100 kilo ohm is all that you are getting across. Okay, what is your preference will be? At least mega ohm or plus. Okay, so either you look for larger VA, that means essentially look for good eta value, smaller eta value, 0.0004, 404 or 406 kind of. Okay, that's the idea behind the search. Okay. There another resistance is worrying me. You know, after all, you have a base collector junction. Is that correct? In a transistor, you have a base collector junction. So if you see between your base and collector, there is a junction. Is that okay? Is that point clear to you what I am talking about? This is my base, this is my emitter, and this is my collector. Okay. Emitter, collector, base. Between these two terminals, base and collector, there is a junction, there is a diode sitting there. Which is the normal operation? Diode will be in what operation mode? Reverse biased. A reverse bias diode, what is the IV characteristics in reverse bias? Typically if you see I versus V, very small slope. Practically saturation current is the order of picoamps or lower, so the slope is very low. Okay, very low. If that is so, if I take the delta VC by delta IB, which is VC by IC by RB, so I get R mu by same simple method. R mu is beta times R0. R mu is beta times, and R0 is related to what? Early voltage by collector current. Okay, so I know this. Will you think R beta is how much? Not less than 100 normally. R0 is how much we calculated just now? Hundreds of kilo ohms. Okay, into 100. So how much it is? Tens of mega ohms or above. So in between if this resistance R mu is greater than tens of mega ohm, will it have any influence or will not have influence? Between two nodes, if I short circuit, that is R is 0, everything at the input will pass to the output. If the resistance is very high, you can say as if collector is separated from the base, but it is not zero, it is not infinite resistance. So there is a connection between output and input, whether you like or you don't like. Is that clear? So R mu may be hundreds of mega ohms or tens of mega ohms, but it exists finite value. Okay, is that point clear? So we must know how finite is that finite value. So that's why we calculate beta 0 times R0 as your R mu. Where is it exist? Between collector terminal and base terminal. Base collector junction reverse bias will give you a high resistance, which is called R mu. Yes. Just now I said it's a diode, reverse bias diode. Capacitance क्या होता है reverse bias diode में? Even at zero bias, junction is called forward bias, reverse bias. Even at zero bias, junction is always reverse bias. There is a built-in voltage there sitting there. Is that correct? There is a built-in voltage sitting there. So the diode is even at zero bias is equivalent of, because there is a depletion layer intrinsically present. That value epsilon A by depletion layer width is the capacitance. Epsilon A by D is capacitance. Now the problem is, if I apply larger VCB, this depletion layer will increase or decrease? Increase. That's what the reverse bias is. The capacitance will decrease. Is that correct? So we say this capacitance is function of reverse bias, whatever VCB I apply. Okay. So I say this junction capacitance is Cj0. What is Cj0? At zero bias capacitance, that is the depletion width at zero bias at the built-in voltage, and this V is the applied reverse bias, and phi 0 is called built-in voltage for the junction, which is Kt by Q ln Ne Nd by Ni square. So we may say for the transistor cu mu is cu mu 0 1 minus VCB by phi 0. This half is not very correct. Why it is not every time correct? Device theory says if it is a step junction, it is half, it is linearly graded 1/3 and or 0.3 or something. Exponential it will be further different in values, but assume right now the way either of. So I write n normally will be either linearly graded, exponential is always assume linear. Okay. Or actually it's not error, it's not a exponential, the function which you get there is called complementary error function. Okay, we will not look into math right now. And for that 1/3 0.3 value is, or 1/3 value for n is good enough. Okay. So if I am given cu mu 0, I know phi 0, I know the VCB I am applying, then I can get cu mu value. Is that clear, everyone? This is like a diode capacitance, nothing great. Okay. So where is that diode capacitance will sit? Where this diode capacitance will sit? It will be across R mu. Is that clear? It will be across R mu. So you have in between base and collector there is an RC, parallel RC sitting there, R mu and C mu. Does that give you some value? R mu into C mu is what? Frequency term or some time constant. So input से output में कहीं ना कहीं time relationship है अभी, और ये घातक भी हो सकता है. इसको बोलते हैं फीड फॉरवर्ड और फीड बैक. इधर से इधर आ सकता है और इधर से इधर जा सकता है. So we want to know what is happening now. Earlier what we thought, input and output are separate. Now these two have suddenly brought worries to us. अरे यार ये तो connection है. So we must know how much is that. If this is very large impedance, so well and so good, fantastic. C mu is very small, R mu is very large, fantastic. That is ideal. But if it is not, then how bad it is, I must know. Similarly, you can also see there is a base emitter junction is also there. What emitter capacitance we calculated first? CBE. which was it? Diffusion capacitance, charge variation. But apart from that, there is a base emitter junction which is forward bias. Please remember, base emitter junction is forward bias. So if I write this standard relationship like Cj is equal to Cj is 0 on this, am I right? Because here Vb is not negative now, Vb is positive. So this kind of, because depletion layer actually may be very small or even negligible, because you are forward biasing the base emitter junction. So normally one doesn't evaluate like a reverse bias diode any capacitor. I just want to show you why I did it. This is normal reverse bias capacitance calculations. We see this will be negative, this term will be positive, so C will keep falling. Is that correct? Now we say we don't know exactly what is happening because depletion will collapse smaller and smaller. We don't know exactly how, it's not linear proportions now, not even 1/3, not even half laws. So we have now figured out over the experiments, hundreds of them, you can assume this CJE typically twice that of CJE0, which is 0 bias whatever capacitance you have of that junction, twice you use it and that's good enough. This is our, what is it called when you do without any great physics on that? Empirical. By lot of measurement and lot of intuitions we figure out generally twice the CJ0 is sufficient for accuracy. Is that correct? So what will specify you? CJ0. But when you write CJE, you should multiply it by 2. Okay, that's the another value. So what is the input capacitance now you have? You have two capacitances at the base emitter junction. What is the first one? The diffusion capacitor. What is the second one? Junction capacitor. So that total input capacitance is named as CBE plus CJE. Is that correct? The total input capacitance is between base and emitter is C pi. Across this is R pi. So have we taken many effects of actual transistor on the input side? We got C pi, we got R pi, we got R mu, we got C mu, we also got GM, other side we also got R0. So almost everyone is considered, but few quick things about this. If you see a bipolar transistor in real life, it has 4 layers and not 3 layers. Okay. We make transistor in one substrate. This is one transistor, there will be another transistor, N transistor in the same substrate. So the collector is here, base is here, emitter is here. So there is a 4th layer which is called substrate. So it is NPN and there will be P epi layer or substrate layer. So there is another junction sitting. Do you see that junction? Which is the junction? Collector substrate junction is also there. Is that correct? Normally I will short circuit substrate, but still there will be reverse bias for it. Is that correct? Now that means additional capacitances, even resistance, but that normally is very high. So at least CS must be calculated, CJ, collector to substrate capacitance, which will follow like a diode law. Say diode, so we write CJS, CJCS is CS, CCS0. So whatever voltage between collector and substrate, using that we must again calculate the capacitance said, which is, if this terminal is 0, will it go to emitter then? In common emitter circuit, emitter is grounded. Is that correct? But internal emitter is not grounded, there is something else is coming there. So we say this capacitance must always be grounded and not taken to emitter. Is that clear? I just tell you what I am saying. This capacitance from collector junction must be grounded independent of whatever you are, because substrate is going to be grounded bias. Is that correct? So a CCS is capacitance between collector terminal and ground, is called CCS. हो गए सब कैपेसिटेंस हो गए, अभी फाइनल 3 रेजिस्टेंस रह गए और उसके बाद सर्किट. Since these are diffuse regions, any semiconductor will have some resistance. Is that correct? Take a bar of a semiconductor or any material, rho L by A. There is a resistance sitting there. Is that correct? R is rho L by A. Each regions will also have some resistances of its own. Is that also added to it the contact resistance of metal with that layer. So there is a resistance associated with emitter, resistance associated with the base, and resistance associated with collector. These essentially are called RBB dash, RES and RC. Is that clear? Collector, why it is called? Because collector external pin to internal collector there will be a resistance, external emitter to internal emitter there is a resistance, and similarly for the base. So if I use this, final word for the day is this. Okay, this is the final circuit. You can see we start from the base, the lower side is emitter, this is external collector. So this is the end of the, all that we did is the equivalent circuit of a bipolar junction transistor. So all the terms we have derived, is that clear? Every term which I wrote here, I have explained why they are coming and what will be their values. Okay, is that clear? Only thing you should know what I just said, there is a B dash, C dash and E dash term. This is called internal emitter base collector points. These are B, E, C are external. In between there is a resistances as I shown here, RBS, RES, RBB dash and RC. Okay, is that correct? If you leave that, this is the equivalent. Otherwise, the actual equivalent will be have RC, RBB dash as well as RES. Is that okay? This equivalent circuit, wherever transistor will appear in an actual circuit, between these terminals I will just replace this, okay, and then solve the Kirchhoff law with external components connected here, 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 wherever it is. Is that correct? Some more loops, some more nodes, solving. Okay, is that okay?